Okay, so as I said, we're talking about randomized experiments compared with observational studies. We see our targets here differentiating between the two and being able to implement appropriate experimental design to reduce the bias and any chance variation that we see. Okay? We just saw that with our farm sampling activity. There was variation across all of our samples. Ideally, if we can take steps to preemptively reduce that amount of variation, like if we could foresee that that stratified by column sample is going to get us the best results, the most accurate results with the least variation, we'd like to be able to do that. So we're going to look at some procedures to maybe help us reduce any chance variation and reduce any bias that could seep in to our analysis. Here's a little bit more of an outline of some more specifics here, if you need to look back at that later. But this is really getting down to the heart of statistics right now, with this idea of an observational study versus a randomized experiment. Okay? An observational study is observing individuals and measures the variables of interest, but it does not attempt to influence the responses. And the purpose of an observational study is to describe some group or situation. So think about this. You're observing what people choose to do on their own. Now that can be good because people are doing what they want to do. You're observing them in their natural environment, their natural habitat. But it can also have some limitations in the conclusions that you can make. Okay? We'll talk about those momentarily. A randomized experiment, on the other hand, it deliberately imposes some treatment on the individuals, and then you observe their responses, their reactions to that treatment. The purpose of an experiment is to study whether the treatment causes a change in the response. There is that important word that we've been building up to. Okay? Up till now, we've been saying like causation. Like, oh, be careful with that word. You can't say one thing causes another. Well, today, by the end of class, we're going to see the pathway that you need to take to show causation, to be able to prove that one thing does in fact cause another to happen. Okay? Now, with the experiment, we have more control. Okay? As the researcher, we are more in control. Okay? As I said with the observational study, you're just kind of like looking at the setup and letting people do their thing, and you're sitting back and just watching what happens. With the randomized experiment, you are assigning people to do this or to not do this. And you as the researcher have more of a manipulative hand in the whole process. When our goal is to try to understand cause and effect, experiments are the only source of fully convincing data. You need to do it. If you want that possibility of concluding a cause and effect relationship, you have to do it as a randomized experiment. Yeah. The distinction between observational study and experiment is one of the most important in statistics, as I said. It's also one of the most misinterpreted things by people who do not understand statistics. Okay? You see this with the media, where something is clearly done, a study is clearly done as an observational study, but the media misinterprets the results and the conclusions like there is causation. Okay? Like this is actually causing something else to happen. And you cannot get causation from an observational study. Now, You might be thinking that if you can get causation from a randomized experiment, why not just do everything as a randomized experiment? Well, ideally you would like to, but we have some restrictions and some limitations. Can't always do it like that. The big one is a lot of times randomized experiments would be unethical, okay, or impossible to assign people to receive some specific treatment. One of the things I have linked on my Canvas page for this week is the video for Against All Odds about showing causation, and it looks in great detail at smoking and lung cancer in this country. That it's taken decades to come to the consensus that yes, in fact, smoking cigarettes does cause lung cancer. Okay? That conclusion has taken a long time because it's unethical to do that as a randomized experiment. You can't say, all right, I have my participants, you need to smoke a pack of cigarettes every day, and I'm going to follow you for the next 40 years and see if you develop lung cancer. You can't do that. Okay? You can't ethically assign somebody a detrimental treatment that you might suspect could cause harm to them. We'll talk a little bit more about ethics next week. But you can't ethically do that. So instead, you have to do this as an observational study, where you're following people who choose to smoke on their own. And you're following them over time and see if they develop lung cancer. Now, the problem with that is that you have other behaviors that start to seep in. And we'll talk about those. Those are the lurking variables that we've mentioned before, but we'll talk in more detail about them. Other things, that some explanatory variables are inherent traits, and you cannot randomly assign them. Okay? Like if you're doing a study about like if left-handed people or right-handed people are more likely to do this or that, you cannot assign them to be left-handed or assign them to be right-handed. Okay? Different gender studies are like that as well. You need to do that as an observational study with that limitation in mind, is that your conclusions at the end of it, you might be able to say that there's an apparent relationship between these two things, but you cannot use that key word that this causes that to happen. I also want to put a third thing on here, okay, which we'll talk more at the end of our lesson about this as well. But how practical our results are. Practicality. I probably spelled that incorrectly, but you know what I'm saying. Practicality of our results. Maybe the treatment is not unethical to impose on somebody, but would somebody really choose to do this on their own? And is it practical? Like you might see this in terms of like a diet study. Okay, a diet and looking at a response of losing weight. Okay? You might be able to come up with some really well-designed diet. And you see meaningful results in that response. But there might be a difference between this person following this very regimented diet for 3 months versus choosing to follow this diet on their own for the rest of their life. Okay? There might not be that practicality as a part of it. Okay? So, in that case, you might want to choose to do it as an observational study, where these are people who are electing to follow this diet on their own, okay, with the recognition that other influences like exercise habits, lifestyle, sleep, things like that could also influence those results that you don't really have much control over if it's done as an observational study. So it's not like you're going into something and saying, well, I need to do it as a randomized experiment because I want to get the possibility of causation at the end of it. Sometimes it happens, but other times you might be okay with sacrificing causation in terms of just, it's more practical to do it as an observational study. Any questions on this so far? All right. Now, as I said, the big problem with observational studies are these lurking variables and the confounding that they bring into this process. We know that a lurking variable is a variable that is not among the explanatory or response variables in a study, but that may influence the response variable. And if something is confounded, that's when two variables, typically the explanatory and a lurking variable, or you might have multiple lurking variables, they're confounded when their effects on a response variable cannot be distinguished from each other. So I was just talking about that diet example. We said that lurking variables of exercise habits, motivation to lose weight, motivation to follow this diet to a T, lifestyle, sleep, stress, living situation, all of these things could impact those results and confound them. That if you see a significant difference at the end, or an insignificant difference at the end, because all of these things are kind of combined together, you can't isolate that it was the diet that was the cause of this. Maybe it was the diet and the exercise, or mostly just the exercise, or the lifestyle that this group tend to. These confounding variables, these lurking variables, tend to cluster together. That's not surprising. Like you see somebody with good dietary habits, a lot of times they have good exercise habits, good sleep. Like that's a conscious thing that they follow. As to somebody with poor dietary habits, not surprising that they have poor exercise habits or poor other things. Like these things kind of go in clusters with one another. Observational studies of the effect of one variable on another often fail because of confounding between the explanatory variable and one or more lurking variables. Well-designed experiments take steps to avoid confounding. And the key as to why the experiments, you don't have to worry as much about this, it's in the randomization. Okay, you have all your participants, and you're randomly assigning half of them to follow this diet, and the other half to either follow some more practical diet or choose to eat whatever they want, their normal diet. Well, those behaviors about poor exercise habits, bad exercise habits, those are also being randomly distributed between the two. As long as your sample is large enough, that should be balanced out. Lifestyle habits, okay? Motivational habits, those should be randomly balanced between the two groups as well. Okay? I said it before, we put a lot of faith into that randomization. Okay? That it's going to balance things across the two, or across all groups. So that at the end of this study, if I see a big difference between the results of one group and the results of the other, I can isolate that the only difference between these was that diet. Okay? All of those other lurking variables, okay, that confounding, is not an issue with the randomized experiments. Okay? Leaving the pathway clear to possibly get causation. That's a big idea right there. I have an example here where there's a study that looks at the relationship between smoking during pregnancy and a child's subsequent IQ a few years after birth. Okay, so the child's like 4 or 5 years old now, okay, takes an IQ test. The explanatory variable in this case is whether or not the mother smoked during pregnancy. The response variable would be the IQ of that child when the kid's like 4 or 5 years old. Would this be done as an observational study or a randomized experiment? Please, somebody say. John?
Observational study.
It would have to be observational. Why?
Because you can't force a mother to smoke during her pregnancy.
Yeah, this is clearly an ethical thing that we cannot assign a mother to smoke during her pregnancy, okay, because of the suspected health impact that has. Okay? So instead, you have to observe mothers who are doing this on their own. And as that sacrifice, you go into this knowing that you cannot get causation at the end of your study. Okay? But you can possibly identify lurking variables. Okay? Women who smoke also tend to have poor nutrition, lower levels of education, or lower income. All of those could possibly explain a lower IQ score for that child, either because of those things, those influences during the pregnancy, or during the first few years of life after the child was born. Mother has poor nutrition, baby's probably going to have poor nutrition as well. Okay? Maybe not valuing education as much. So that IQ, those first few years, might not be as high or as incentivized to get that IQ as high as possible. And we know that income can have a lot of influences all over the board. So those confounding variables cannot really be accounted for as an observational study. Now, the best you can do is try to keep track of possible confounding variables. Sometimes specific interactions occur over the course of an observational study. An interaction between explanatory variables occurs when the effect of one explanatory variable on the response variable depends on what's happening with another explanatory variable. Okay? You could have multiple explanatory variables, or this could also happen between an explanatory and a lurking variable. In this smoking during pregnancy, we found exercise to be an interacting variable. If smoking during pregnancy reduces IQ when the mother does not exercise, but raises or does not influence IQ when the mother does exercise, we would say that smoking interacts with exercise to produce an effect on the IQ. So what they found, of those mothers who smoke during pregnancy, if they exercise as well as smoke, there was no noticeable difference in the IQ of their children versus the non-smoking mothers. They did notice that the mothers who smoked and did not exercise, that's where they saw this significant difference between the IQs of the children a few years down the road. So, exercise interacts. Okay? We see specific differences in the results if that variable is present or it's not. Okay? That lurking variable interacts with the explanatory variable. Now, in an observational study, you cannot control that, but you can keep track of it and present the results differently and separately. Okay? If two variables interact, results should be given separately for each combination. You're trying to be as forthright and honest as possible. Okay? So at the very least, you see this interesting discrepancy here. Include that in your conclusions. This slide just goes over a little bit of the vocabulary of the observational studies and the randomized experiments. Okay? Most of these words are pretty straightforward. You know what these words are. It's not like it's a fine statistical definition here. In an experiment in which we do something, the treatment is that action that you're subjecting the participants to. Okay? Either people, animals, or objects, okay? And then you're observing the response. Okay? We already know that the explanatory variable compared with the response variable. The individuals studied in an experiment are oftentimes called the subjects, particularly when they are people or animals. The explanatory variables in an experiment are often called the factors. So you could have multiple explanatory variables in a single experiment. And those are the different factors that are contributing to that response variable. Okay? So the treatment is any specific experimental condition applied to the subjects. So if there's more than one factor, a treatment is a combination of specific values of each factor. So if you have like 3 different factors, and factor 1 is present, factor 2 is not present, factor 3 is present, that is a specific treatment. As opposed to the next treatment where all 3 of those factors are present. And a different treatment where the first 2 are missing and the third one is present. So you could come up with a number of different combinations for your treatments. Now, we did say that an experiment has the possibility of concluding causation. The one thing causes this change in the response variable. That doesn't necessarily mean that everything is good or smooth sailing from there on out. Okay? Experiments don't guarantee good data. We saw that a little bit with our farm example. Okay? If we accurately follow those sampling methods, we're doing our best effort to try to ensure that we get good data and make reasonable conclusions. There's no guarantee of that. Good designs are essential for effective experiments, just as they are for sampling. Okay? You need to be on top of it every step of the way. I have an example here. A college regularly offers a review course to prepare students for the GMAT. So this is like a graduate school SAT, right? So at the end of your undergraduate college, if you want to go directly into graduate school, then a lot of schools want you to take the GMAT as preparation for that. So usually this is offered in class, and there's also an online version. But for some reason, this year, the class is only being offered online. So you're looking at your students, okay? Those are the subjects, those are the participants. The treatment here is the online course, which this year, all of them are being forced to take. If you want to take this class, it must be the online version. And the response variable would be the GMAT scores that they get. Now, if you find that the results were 10% higher than the long-time average for those who took the classroom review course, it might be tempting to conclude that, well, the online course is the way to go. We're getting better results, 10% higher results with the online format this year, as opposed to what we've seen over the past years when it's been both online and in the classroom.
So basically, it's just because we get the same people who are taking that would be taking the in-person one or taking the online. not a control group, basically.
Exactly, yeah. So we've got nothing to compare it to. Connor said there's no control group. Okay? Everybody's online. So you're getting the good and the bad. In this case, the results are a little bit higher than what they've had in the past, because what you're comparing it to is the past. It's not really a fair apples to apples comparison. Right? You want the control. If this is a randomized experiment, you need to have something to compare it to. Okay? We can't really effectively conclude that this course is better than the previous versions. Yeah, I'm not going to read all of this, but this kind of goes into more of the detail that Connor was able to identify. And the review course showed students in the online were quite different from the students who in the past took the classroom course. Okay? In particular, they were older and more likely to be employed. Okay, you're taking an online class because maybe it's more convenient for your schedule if you're also balancing a job, as opposed to the students who were like undergraduate students and they're full-time students, so they're on campus, they might as well take the in-person version. An online course appeals to these mature people, but we can't compare their performance with that of the undergraduates who previously dominated the course. The online course might even be less effective than the classroom version. The effect of an online versus in-class instruction is confounded with the effect of lurking variables. As a result of confounding, the experiment is biased in favor of the online course. Okay? So, introducing some lurking variables here: age, okay, possibly motivation. They are already employed, so you might have some street skills. I mean, you hear about like book skills versus street skills, and book smarts versus street smarts. Messing up my cliches here. But those could be possible lurking variables. So we also see some cases where many times laboratory experiments use a design like this. Okay? Where you have the subjects, you're subjecting them to the treatment, and then you're measuring the response. But the real world isn't a laboratory. It's not as perfect as these artificial settings sometimes. The laboratory, these simple designs often work very well. But the field experiments and experiments with animals or people deal more with variable conditions. Okay, outside the laboratory, badly designed experiments often yield worthless results because of the confounding. We're going to talk about an idea called ecological validity. And you see that word, the ecology, the setting. Ecological validity is when the results that you get in an artificial laboratory setting don't carry over to the real world. Okay? Because you're not accounting for other impactful variables that are in the real world that you can't replicate in the laboratory setting. And when I say laboratory setting, it's not like a scientific lab necessarily. It's an artificial setting. Okay? An example of studies that might be impacted by ecological validity are sleep studies. A lot of times with a sleep study, okay, they'll bring you into the laboratory, okay, have you spend the night, you're hooked up to machines, okay, and they track breathing or snoring or whatever. Well, are you using that one night sleeping in the lab with all this equipment strapped to you to represent your normal sleeping habits? I don't know that any results from that sort of a study, it might not have ecological validity, okay, because it's not in the everyday kind of setting that you're used to. So keep that in mind as you're not only performing your own studies, but when you're interpreting the results of other studies, existing studies. It's something to keep in the back of your mind. Now, randomized comparative experiments, okay? I said we put a lot of faith into that randomization. The remedy for confounding is for a comparative experiment. Some individuals receive one treatment and similar units receive another. Most well-designed experiments compare two or more treatments. Now, some experiments may include a control group. Connor had brought this up. Okay? If we're trying to show how good the results are for this one group, well, how good is it? We need something to compare it to. That is the control group. And we don't want to compare it to the past or something in the historically what has happened. No, we want our own control group that we can make our own comparisons, because we want everything to be as balanced and even as possible between these two groups that we're comparing. Now, that control group oftentimes receives an inactive treatment or an existing baseline treatment or a placebo. You've probably heard that word before. And if you're taking psychology or you've taken that in the past, okay, you might see some overlap in what we're talking about today. That's good. I've been saying from the beginning that I want you to value this class not for just what it is on its own, but in how it can impact and influence and tie in with other courses that you're taking. Okay? A placebo is supposed to be similar to an active ingredient, okay, another treatment, but there's no reason as to why that should work. Now, typically this is a pill. Okay, if your experiment is done by group A, you're going to take this pill and I'm going to measure whatever. And group B, you see group A get their pill, and group B, well, how do I expect anything to happen if you're not going to give me anything? Okay? So they give you a placebo, okay, which appears like the active thing, okay, but there's no chemical ingredient to it that should make it work like that. It's a sugar pill is the general term that's given. Now, you're following these results because they don't know which group they're in. Did I get the actual ingredient, or is it the placebo? To show effectiveness of a new drug in this country, the FDA wants to show that it's better than the placebo X number of times, and by this magnitude. I have a little video that I'm going to show you next week on Monday that talks about placebos and the placebo effect. Okay? The placebo effect is when people take something that should not give them any result, but they see a result. Okay? Now, sometimes this happens. It's that the mind works in weird ways. And you might have seen this in psychology. That just that action of taking something, even if there's no chemical reason for it to be working, the body sees change, sees results. And if you're seeing these results with the placebo and with the chemical drug, what's really instituting that change? Is it the mind or is it the chemicals? The FDA wants to see effectiveness at a higher rate than the placebo. Now, as I said, placebos are usually pills. Not always. One of the things that you're going to see in this video is a placebo surgery for people who have chronic knee pain, where the actual surgery, you go in and you loosen some ligaments or some tendons or whatever. But some of these participants in this study, they underwent, unbeknownst to them, a placebo surgery, where the surgeon opened their knee and then immediately stitched them back up. And many of those patients reported feeling better. They thought they had the actual knee surgery. Okay? They just had a little bit of a scar there, and that's all that happened. And there's the placebo effect that's playing into their results. And it starts to, it's weird how the human mind works. Yeah, so I'm getting ahead of myself. That's a whole interesting wormhole in itself that we can dive down. But we'll take a look at that on Monday. It's a story from 60 Minutes from a few years ago. Now, in these randomized experiments, they're using that comparison of two or more treatments and the random assignment of subjects to these treatments to make this comparative randomized experiment. Okay? That's kind of like the gold standard for what we're working for. Now, the comparison alone isn't enough. If the treatments are given to groups that differ greatly, bias will result. Okay? Let's say I collected my group of participants, and people are mingling for a little bit. Okay, they come in at 8 a.m. I don't get started until like 8:20. Okay, they're kind of collecting together. Maybe some participants know each other and they're talking to each other. A little small talk. And then I have all my group of participants and I say, all right, down the middle here, this is group A, you're going to receive this treatment. This is group B, you're going to receive this treatment. That has a potential for bias because you might think that it's random, okay? But these people are kind of grouping off into similar characteristics. Again, if they know each other, okay, they may have similar behaviors, similar attributes. You don't want to do that. You're putting a lot of faith into the randomization. Random assignment means everybody in your group has a number. Get your random number generator out, and you're randomly assigning participants to the group. So person number 3, person number 12, person number 37. You're in group A. These other people, you're in group B. And that is the random assignment. If we were looking at that GMAT example, okay, you have your experimental units, which would be the students who are taking this GMAT preparation course. Half of them, okay, 50 is the sample size, half of them are randomly assigned to group 1, where they will get the online course. The other randomly assigned 25 students, they are going to obtain the classroom course. You get the results, you get the GMAT scores, and that's where you make that comparison. Okay? There's that randomization of the treatment. Now, the logic of these randomized comparative experiments is that random assignment of subjects forms groups that should be similar in all respects before the treatments are applied. Okay? Going back to the diet example, it's like I said, okay? Some lurking variables like exercise, lifestyle, stuff like that. Good exercise habits, bad exercise habits. You should have some of both in each group. Lifestyle, same across both groups, where the only real difference at the end is that treatment that they receive. As long as that sample is large enough. A comparative experiment with randomization ensures that influences other than the experimental treatments operate equally on all groups. Therefore, differences in average response must be due to either the treatments or to the play of chance in the random assignment of subjects to the treatments. Okay? We saw that even with that randomization, sometimes you might get pockets or clusters. Okay? That can be assisted with the sample size being large. Okay? Any chance variation that you have, okay, should stand out as being an outlier or whatever. You work through it, the bulk of that data is there. But if you have a small sample, okay, it's harder to identify that chance variation, work through that chance variation. So the principles of experimental design. Okay? You have control in a randomized experiment. The control affects the lurking variables on the response, most simply by comparing 2 or more treatments. You're trying to randomize whenever possible. Okay? Use that chance to assign subjects to the treatments. And replication. Use enough subjects in each group to reduce the chance variation in the results. If it's a small sample, okay? If I just have 2 people in this group and 2 people in this group, I mean, who knows what's going to happen across those group of 2 people? As opposed to if I have 200 in each group, I might get a bizarre off-the-wall result. Or I might get somebody who's working out.
Please report to the assistant principal's office at the bell. Thank you.
Who? So if you have a larger sample, you're more likely to get accurate, representative results. Now, our goal, and I'm a spoiler alert here, our goal is statistical significance. An observed effect so large that it would rarely occur by chance is called statistically significant. Okay? It's not just a little bit better with your treatment group over your control group. Okay? It's large enough that we can say that it would be unlikely to get this due to chance alone. Okay? Now we're filling in the gaps here. Okay? We need our unit on probability, which is coming up next, to be able to quantify this and determine how large is large enough. And if a mistake was made, like what is the likelihood that it is chance variation? Okay, we need an understanding of probability in order to do that, and we will have it. Okay, but if we see this significant difference, okay, it's said to be statistically significant. A statistically significant association in data from a well-designed experiment does imply causation. This is how we get causation. That's our goal from the beginning, to say that this explanatory variable does in fact cause this change in the response variable. You can only get it through a randomized experiment and observing a statistically significant difference from that randomized experiment. All of that needs to happen in order to get that implication of causation. That we can be pretty sure that this thing is the one and only thing causing this to happen. Now, we got a lot of gaps to fill in there between now and the end of the year, but we made some significant strides today. Okay? And we're not done. I got to finish this lesson on Monday. Okay? But we'll get there. You do have a homework assignment that I posted due next week. If you wanted to start chipping away at that, you can. All right. I think I have it set due Tuesday. I know you're not in school next Wednesday or remote Wednesday, whatever. You don't have it. Yeah, keep that on your radar for next week. Any questions right now? All right. Thanks, guys at home. Good to sign out. We'll see you.